Right, question 14, the wheelchair question. An electric wheelchair is powered by a battery, allows users to move around independently. Right, one type of electric wheelchair. It's got a mass of 55, the user's got 65. Okay, it can travel level ground for 12k at a speed of 1.5. Right, battery. Right, this is immediately mixing up electricity and mechanics. So, yeah, honestly, be ready for that, or don't panic, whatever you do when you see this. Right, so we've got an EMF 12. Doesn't mention internal resistance, so we can just assume that's the supply voltage. It's going to discharge fully and discharge that much charge, and the power outputs 100 watts. Right. Can't see any time there. Right. If we've got power and we've got charge, we could really do the time, couldn't we? So, but looks like we can calculate the time. Right. So, but yeah, it's going to, on a full battery, it can travel 12k. And during that journey, it will discharge this amount of charge. Okay. If we knew the time, we could work out the current, because we know the voltage, and we can use P equals IV. Well, if it can travel at that speed for 12k, we can use speed equals distance over time. So time is distance over speed, so it's 12,000 over 1.5. Right, that is 8,000 seconds. Now, do we need to get that into minutes or hours? No, because we're using that value in an equation, so it needs to be in standard units. We're going to leave it in seconds. Okay? Right. I is equal to Q over T. Again, this is a question. Our recall of the core equations, the defining equations, has to be instant. Yeah, we haven't got time to go, what's the equation for current? Or what's the equation for power again? It should be there. So we've got the charge, which is, now we've got 7.2 times 10 to the 4. 7.2 times 10 to the 4 coulombs divided by 8,000. That's given us a current, a constant. We're going to assume a constant current from the battery of 9 amps. Okay? We know the voltage, and we also know P, electrical power, P equals IV. So current is 9, the voltage is 12. That comes out as, don't write down 100 watts. Okay, please. The question says about 100 watts. We have to write the correct answer. Okay, so the correct answer is 108 watts. And finally, please, we don't have to then say which is roughly equal to 100 watts. We don't need to write that. An examiner will know that 108 is close to 100. They've done some maths before, trust me. Right, there you go. During the journey, the force due to friction and air resistance acting on the wheelchair. Assume that all the energy available in the battery is used to move the wheelchair forward. Okay. Calculate the total mean resistive force. Right, so it's going to move at a constant speed, because it says that at the start, doesn't it? Constant speed of 1.5 on level ground, 1.5 meters per second. Calculate the mean resistive force. Now, this is one of the most underrated equations in mechanics, and that is P equals FV. Well, when to use this equation, right? So power equals force times velocity. This is when something moves at a constant velocity. Okay, it moves at a constant velocity, but we need power to overcome a resistive force. Yeah, that's when you use that equation. That's where that equation comes from. So I'll just repeat, that's when you're moving, so the object's moving at a constant velocity, but we still need power to overcome a resistive force. Yeah, simple. Right, now the power is, we're going to use our value of 108. That's equal to the resistive force F multiplied by the speed of 1.5. Now that gives us a resistive force of 72 newtons. Okay. Mean, because obviously this is assuming it's going to be a constant speed. Right, wheelchair is now going up a hill. Okay, the wheelchair user then travel up a steep incline of 15 degrees to the horizontal, shown in the diagram. Calculate the component of the weight of the wheelchair user downhill. Right, his weight is vertically downwards. Okay, this is a very common question when you have things moving up inclines. Now, weight is vertically downwards. However, it's very common, or it's very useful, to split the vertical weight into two perpendicular components. One parallel to the slope, one perpendicular to the slope. Now, this is actually, admittedly, this is a little tricky to visualize, but it does take a bit of practice. Okay? Now, we've got a component of mg that is perpendicular to the slope. Okay? So we've got a right angle there. Okay? So that is one component. There's going to be another component down the slope. Okay? That's at the weight. Now, I've drawn them like that because the two components should be the two sides of that rectangle there. Yeah? The component, although it's vertically downwards, the component is the diagonal. Okay? Now, which angle is which? Right? Now, it doesn't take, or it's a little bit of geometry should show you that it's this angle here, which is 15 degrees. Right? Now, if that's 15 degrees there, then the component which is perpendicular to the slope is mg cos 15, because it's perpendicular. So because it's adjacent to the angle. Now, the component, which is the one we want, which is down the slope, the component of the weight, which is down the slope, that's this one up here, which is mg sine 15. That's the component we want down the slope. So, mg sine 15 degrees is equal to what? Combined mass, we've got 55 plus 65 times 9.81 times sine 15 degrees, which is, okay, 305 newtons. Okay, that is question 15. Thank you.